Well, welcome everyone to this afternoon's environment seminar. People are just logging in, so hopefully we'll get a few people coming through in the next couple of minutes. So my name is Matt Hipsey. Welcome to this afternoon's seminar. We're pleased to introduce Don White to you. He's a forest ecophysiologist working for some time, 27 years at CSIRO in forestry and ecosystem sciences. And more recently, since I guess the last almost decade,
7 years, yep.
7 years working in some forest science applications in the catchments of Chile, which we're going to hear about this afternoon. So thanks for logging in. I'm just going to monitor the chat. So if you have any questions, we can ask them to Don as he's finished. And please just raise your hand if you have anything you would like to request. So with that, I'm going to just switch and you should be ready to go. All yours.
Okay, good afternoon. The very odd experience of speaking to a largely empty room and to a microphone and a camera, but I'll do my best. The title is on this slide. I've been very fortunate to, after leaving CSIRO in 2013, I visited Chile during the first part of 2014, and we started to talk about some project ideas. And in the middle of 2015, Richard Silverstein, also from Australia, came over and visited, and we developed a project which commenced at the start of 2016 and has been running pretty much full-time ever since. It's concerned with the effect of plantations on water resources, and in the Chilean context, the baseline is the natural forest rather than pastures and other agricultural land uses, which is often the baseline for water balances here. So I thought I'd just show you 2 or 3 slides, a bit of a Chilean travelogue, because people sort of say to me, why Chile? Why do you spend so much time in Chile? Well, the first and most obvious thing is the landscape. And this image that you can see here on your screen is taken, we lived and worked in a city called Concepcion, and on a Friday afternoon, we work 45 hours a week, but it's early knockoff on Friday. If you leave the office at 3 o'clock, you can arrive here 8 or 9 o'clock, have a nice glass of wine at the Refugio Tinquilco in Parque Nacional Huequehue. And then in the morning, you can get up and have a lovely relaxed breakfast and walk for about 3 hours and be exactly there, looking across at the Volcan Villarrica, an active volcano, about 3.5 hours drive south of Concepcion, and about 7 or 8 hours drive south of Santiago. So the landscape is one of the attractions. Okay. The other attractive thing about Chile is the people are extraordinarily hospitable and friendly. You can see Richard there in the lovely red jacket, and myself looking a bit thinner than I do now. That's one of the advantages of Zoom, is that it doesn't quite show the girth. These people, Richard and I went for a walk up Chillán, another volcano in Chile, on one of our first trips together to South America. And at the end of that day, we got to the car park and these people were there and they asked us a few questions and we spoke to them in our halting Spanish, and one of them turned out to be an English teacher. And as well as being really rude about my English, they shared their wine and their bread and their cheese, and we sat around in the car park and had a typically lovely time. Fortunately, Richard and I only had about 500 metres to go to our abode, which was just as well, because you can see there's a very large bottle of red. So the people in Chile are almost without exception, extremely friendly and extremely hospitable and welcoming of visitors. And this was a fantastic end to a lovely walk up a mountain. The other thing that was really attractive to me about working in South America was the opportunity to work in native forest. I've spent a career mostly working in planted forest. And here, a very important focus of the work in Chile was to quantify the water balance of the native forest, both at the catchment and the stand scale, and to understand the approximate scale and the mechanisms underpinning any changes in the water balance in these forests. So that was our work. Richard and I didn't work, and that's what I'm going to talk to you about today. Richard and I didn't work alone, and here's a picture of a few of our co-authors. Juan Jose Quiroga is a very excellent statistician, mathematician, also works in ecophysiology. Francisco Bolocchi is now the leader of the project. He joined the project after we'd been working a couple of years and has since taken over as the leader of the project. Francisco Garate is an excellent GIS person and spatial scientist, a good programmer, but also loves forests and being out in the field. And there he is taking some LAI images. Los Tatas, that's the granddads, working there in the forest. And El Queso Grande, the big cheese, that's Pablo Ramirez. He's an ecologist, studied in New York, in upstate New York, and is an excellent ecologist and is the leader of the ecosystem research program in Arauco. On to the talk. Well, I suspect I don't need to tell people who have been living and working in Australia, and particularly working in forest sciences, that whenever large-scale land use change occurs, and particularly the establishment of commercial plantations, there's often concern about the impact of that change on water resources, both on the supply of water and on the quality of that water. I'm not going to talk today about the quality of the water, but there is work going on in Arauco on that issue. I'm going to talk, because it's really almost a given that this is something that's important, I'm going to really focus on the Chilean context here and why it's a particular issue for them at the moment. And then I'm going to talk about the project that we've been working on, how we've set it up, why we're doing it, what it aims to do, and where we're working and how we've designed the experiment. And then I'm going to present some results. We've worked on a lot of sites. I'll be focusing today on one of the sites, but if I've got time, I'll just provide some corroborative evidence from the other sites. And then we'll talk a bit about what it means. We're going to start with water balance. We're going to talk about growth. We're going to talk about water use efficiency by focusing on this one site in particular. The issue, this is an image on the right-hand side of Central Chile. If you can see my cursor there, this is Arauco Bay. The city of Concepcion is in here. And up here above the picture, you get to Santiago. And this is the areas where you can see the plantations. That's the plantation estate. That's Arauco's plantation estate, which is the company that we work with. Now, while they have about 750,000 hectares of trees in Chile and about 250,000 hectares of trees elsewhere, there are more than 2 million hectares of commercial wood production plantations concentrated in this area, a distance of about 700 kilometres from the city of Constitution in the northern part of that map to the city of Valdivia in the south. Rainfall increases from about 750 millimetres in the northern part of that map to about 2,500 millimetres by the time you get to the south. There are also east-west gradients, but the dominant gradient is north-south. In the central region around the Bay of Arauco here and around Concepcion and to the east towards the cities of Los Angeles and Chillán, there's a fairly large-scale expansion of the plantation estate going on, and in particular the replacement to supply a large pulp mill in the Bay of Arauco with with material which is from eucalyptus plantations. And when eucalyptus plantations start getting established, people get very antsy about water. So that was one of the particular focuses of our work around the Bay of Arauco and around Conception, was to compare eucalyptus with pinus. Are they different? Both in terms of the total water balance, in terms of the dynamics diurnally, the dynamics seasonally in particular, because the major concern is always about summer flow rather than total flow, because for those of us in Western Australia, this is also a Mediterranean climate with a very dry summer. Well, not very dry by West Australian standards, but dry relative to their winter. Okay, so we had that expansion of the eucalyptus plantations, which created a particular focus for this issue. And community and government, and when you talk to community groups, often they'll say, I don't mind having plantations as long as it's not eucalyptus. So there are lots of preconceptions and ideas about eucalyptus in particular, but about plantations in general. Alongside that, Arauco, the company that we work for, is FSC certified. So its wood is certified as meeting those environmental standards of that certification group. And in order to maintain that certification, there's an annual audit of all of their processes, including water. And one of the things that, while there are 2 million hectares, Arauco has 750,000 hectares of plantations, only 20 to 25,000 of those actually replaced native forest. Most of them have replaced agricultural land. And FSC has mandated that they put back 25,000 hectares of native forest. At the same time, Chile is moving to carbon neutrality by 2050, and forests are seen as a big part of that, and that's going to have water implications for the region. You know, do we put in plantations to store carbon? Do we try and re-establish larger areas of native forest? Do we have some mixed forest? Do we put in a plantation and then have a transition to a native forest? All of those options are on the table, and so understanding the water balances of these different forest types has become a really important issue in Central Chile. So a bit more context and a bit more local context. There are bits of Spanish have stuck onto the slide, but hopefully nothing too important. So against all of this regulation and policy background, oops, I didn't do that. Oop, there we go. There's also a change in the climate in Central Chile, very much like what we've seen in southwestern Australia, where in the last 30 years the rainfall has been much less than the long-term record. And that is more extreme in the north, in the city of Constitution. So that's the north of the plantation estate. Valdivia is the south, Arauco is the centre. So as you go down to the higher rainfall zones, the proportional reduction is less. At the same time as there's less rain falling, water demand has been increasing per capita, and the population has also increased. And there's a general community negative perception. And this is the killer. Well, the major issue for plantation growers is that often the rural communities that live in the coastal ranges where the plantations are established are relatively poor communities. There's not great water storage or water supply infrastructure, and so you have small communities which are dependent on local intakes from streams and wells. And within the Arauco plantation estate alone, there are just over 1,000 water intakes for local communities. And so where there are issues, Arauco enters into dialogues with these communities, tries to develop infrastructure solutions, other solutions by working with those communities. But in order to do that, it needs to have knowledge. And knowledge is a part of the water management strategy in the company that we're working for in Chile. So their strategy for ensuring security of water supply for the rural communities that live in and around their forests has 3 pillars: knowledge, conocimiento, which is where Bioforest, which is the R&D company in Chile, comes in Arauco, which is where Richard and I have worked, comes in. That knowledge should underpin iterative improvement in management, but there should also be an outreaching and a contribution from the company to its neighbours and to the infrastructure that the neighbours need, etc., and to the strategies that they need to improve their own management of their water resources. So those are the three pillars of the Rialco strategy, and they have an active environmental management group, and within Bioforest there's an active ecosystem research group which is led by one of the co-authors here, Pablo Ramirez. Okay, when we started this work, one of the things that became apparent was that, we were going to do a lot of water measurements, but that the company is making decisions about water now. And on an ongoing basis. That's a handy feature. The auto advance, that's terrific. Okay. And what they had been doing historically is wherever more than 40% of a catchment was occupied by plantations owned by Arauco, then they did an analysis, or they took some measurements of summer flow over several years, in fact. If allowing for 30% interannual variability, that flow was less than the annual, was within 30% of the annual consumption, then that was listed as a catchment under pressure, or possibly under pressure, particularly under a future climate. And Arauco has been actively developing management strategies for those communities. That's an ongoing process, but they're looking for more precise information, particularly on the capacity to predict summer flows. Okay. Onto the project. So, bearing in mind that we're contributing to part of the Arauco water strategy by producing reliable and credible estimates of the effect of land use change and the management of plantations on water balance. We have to put productivity in because our managers require us to put productivity in, but our focus has been water balance, if we're honest about it. But we've also been measuring some growth of these forests as well. Importantly, that's to be delivered through local measurement, because when you go and talk to local communities, if you're talking about data from more than 100 kilometres up the road, there's a great scepticism about that, and so you have to have local data. And we're in a process at the moment of internal communication in Arauco at the moment, as well as external communication, because there's a relatively rudimentary understanding, even in the company, of how these forests change water balance, and a lot of buy-in to the myths that are out there, even within the forestry companies themselves. Okay, I'm not going to dwell on the objectives. Our philosophy in setting up this project is there had been a lot of measurements over the preceding 7 or 8 years of rain and stream flow, or the sort of end members of the water balance. But until we arrived, there wasn't a great focus on processes in the forest. And we reasoned that in order to develop a capacity to predict the interactive effects of climate change, and develop strategies and be able to generalise, we needed to understand what was happening between the rain and the stream flow in the forests and how that differed between the forest types. And that's been our focus. Okay, where are we working? Between 2008 and the present day, 19 catchments have been instrumented, from Constitution in the north to Valdivia in the south. 5 of those catchments are in an area around Cavolgo in the lower rainfall area, and the principal comparison there is between native forest and pinus, because once you get up there, it gets a bit dry for eucalyptus. So I'm not going to focus too much on that because I don't have much data for the 3 forest types from that location. When you get a bit drier, when you get a bit wetter as you head further south around Morelos Crucis, we have another 4 or 5 catchments, depending on how you divide it up. And that will be the principal focus of today's talk, those medium rainfall catchments. A number of reasons for that. One is that it's right in the area where the eucalypts are expanding. We have all 3 forest types represented in the experimental infrastructure there. And there was a third reason which has just escaped me. I'll come back to it if I recall. All right, okay. What was the other reason? No, I had a better reason than that, Richard. Okay. Further south in Bajolas Camus, there are another 4 instrumented catchments. They're all Eucalyptus nitens at the moment, and in the future we will be re-establishing native forest in one of those catchments. We'll be continuing the nitens in one, we'll be establishing pinus in another, and we'll be establishing new eucalyptus in another. So once we've got enough streamflow data, a new experiment will be set up there. In Cavolgo in the north in 2017, there was a lot of very large wildfires, and so that has now become a post-fire experiment comparing pinus, eucalyptus and native forest regeneration. And in the south, well, I think there's plenty of water, but that doesn't mean there's not political issues surrounding water. So we have some measurements there, but I don't expect that the plantations are having an important impact on water balance. So I won't be talking about that today. Moving on. Okay. In the 19 catchments, there is a lot of inventory data that the company produces routinely. So there's a lot of information about the growth of forests. But we've established a network of measurement plots where we've measured heights and diameters, wood volumes annually in 60 measurement plots from the north to the south. 29 of those plots have had at various times water balance, where we're measuring the components of the water balance, transpiration, soil measured using sap flow sensors, soil evaporation calculated from a combination of under canopy radiation data and soil moisture data, interception or throughfall measured in those forests. So those are all being measured, as well as a whole range of other things. But I'm going to be focusing on the water balance and the tree growth this afternoon. And that's just to indicate that the data you'll be seeing today comes from those northernmost catchments, because that's where we expect that the impacts are going to be the most important. We're taking a top-down and a bottom-up approach to the water balance. So we have the stream flow data from which we can estimate evapotranspiration, provided we assume that there's no change in storage or we actually measure it. And we measure the components of water balance, and if they're roughly in the same ballpark, then we start to feel like we have some confidence about the water balance that we're talking about. Okay. So I've said that I really relish the opportunity to work on the native forest in Chile. So I'm sure that most of you know what a pinus plantation and a eucalyptus plantation looks like. Just for those plantation people, the eucalyptus are established at 1,667 trees per hectare in Chile and managed on a pulpwood rotation. The pines are established at a variation of densities, but around 1,200, and then they are thinned either once in the drier north or twice when you get down into the south, and then managed for sawlog, veneer, a whole range of other products. So quite different management. The native forests. So this is in the Cavolgo area. So these are the northern native forests. The coastal ranges of the north and the central plantations. The native forests are called the Roble Wallow forests, Roble and Wallow being the 2 dominant deciduous evergreen species in those forests. In the northern forests, the Roble, which is the nothofagus, grows on the ridges and the slopes. And when you get into the valley, you get into more evergreen species, Peumo, Cryptocarya, Avellano, and 9 other species in those forests. These are mixed-age forests. They're fire resprouters, the nothofagus. They will resprout from within the crown after a wildfire, and they will resprout from the base, which is unusual for a nothofagus, but these deciduous coastal forests are fire resprouters, and so you have a very mixed-aged forest. So there are very young individuals, and there are individuals in these forests that are a couple of 100 years old. Okay. The height of the forest, they're not very tall. They're about 12 metres tall on average. So we're not talking grand forests. Okay. When we get down into the middle regions, we still have, so this is the area that I'm going to be talking about mostly today. We still have deciduous nothofagus in the overstory, and you can see a picture of the crown here, which has both the mix of the evergreen and the deciduous Nothofagus obliqua in this case, very closely related to Nothofagus glauca. In fact, for a long time they were the same species, but they're now different species taxonomically. And you can see here, this is in winter, and this is underneath a Nothofagus tree in winter, and this is underneath the evergreen species. And there are mixes of them, but as you get towards the valley in these systems, the evergreen species become more dominant. So while it's a deciduous overstory, the leaf area index only reduces by about 50% in total in the winter. There is still quite a bit of forest. Okay, there are 10 species in all. Okay, this is just to show you the plantations that we measured in were 20 years old. Okay, so they're post-canopy closure plantations. And the leaf area index in the pinus plantations was very similar to the native forest, perhaps slightly lower than the LAI in the native forest, though it depends on what assumptions you make about the extinction coefficient. And the globulus had a significantly lower leaf area index at this age. They have a higher peak at age 4 or 5, and we do have some measurements from younger forest in another site, but I'm not, and I can show some of that later, but it's not the focus. All right, so that's the forests, the terrain, steep. Average, what's the average slope, Richard? 40% and 50%. So this plot here that I've shown, it's very difficult to stand up. In fact, you spend most of the time sliding around on your ass. Very steep terrain. And in fact, this is a remnant of native forest, which is there because it's too steep for commercial forestry, that particular part of that catchment. The soils, the geology is a metamorphosed sediments of the region. And so you've got schists which break up, and you have weathered zones in the plains in the schist that can be quite deep. But the actual mineral soil, while there's weathered material down to quite deep, the mineral soil is very shallow. This is the Cavolgo location. And I don't know if you can see it here. This is all rock. And there's a tiny little mantle of soil on top of the rock, which is full of shattered rock material. There's a lot of quartz broken up in it too. 50 centimetres deep. Sometimes gets down to 70 centimetres deep, but it's about 30 to 40% rock. This is further south where you get to Bajolas Camus and you get a more deeply weathered material. It's much richer soil, much more fertile soil, but I'm not going to be showing you data from that. What we're going to be talking about is these shallow soiled catchments. And that is the dominant geology in the western half of the coastal mountains where the plantations are. When you get into the eastern half of the coastal mountains, where another forestry company has most of their plantations, there are more granite soils, although again, they seem to be fairly shallow as well. Okay, all right. So how to tackle native forest? There's lots of species there. We want to get sap flow sensors in. Which species do we work in? Well, in the Morelos crucis forest, oh, a bit of Spanish has snuck in. Bosco nativo is just the native forest in Morelos crucis. There are 10 species, but 95% of the basal area, and therefore the conducting sapwood area, is 2 species. So I have just measured the dominant deciduous species, the Nothofagus species, and one of the evergreen species, Cryptocarya alba, which makes up most of the rest of the biomass, and I've assumed that all the evergreen species behave like Cryptocarya. Introduces a relatively small area. Same story in Cavolgo, different species, but again, you've got the Nothofagus, in this case glauca, and Peumo, Cryptocarya alba, make up most of the biomass and most of the basal area. The other thing about these forests is that at least on the slopes, and on the ridges, there's not a lot of understory. That's not true in the valleys, where there's often very dense thickets of a native C4 grass called Triskaya. This can be very dense and impenetrable vine-like stuff. but it's only in the wet zone, the very bottom of the valleys where you find that. Okay, so we're going to talk now about Morelos crucis. We're going to talk about the water balance in these forests. We have 9 water balance plots among 21 growth plots. This map just shows you the location of those. This is a pinus catchment, this is a native forest catchment, and this area here isn't in one of our experimental catchments, but it's an area of Eucalyptus globulus. And those are the forests that we worked in. And now I'm going to start showing you the results. So throwfall. And it won't be a surprise to anyone who's worked in Pinus radiata and eucalyptus plantations that there's more throughfall and less interception in eucalyptus than there is in Pinus. 13% on average of the rainfall is intercepted by Eucalyptus globulus, more like 21% in the Morelos crucis area. Roble, Payumo forest, the native forest interception is very similar to the Pinus. And the experience of other studies, I believe there's a study by Andres Irame, which made a similar comparison, and they found a very similar thing, that the interception of the Pinus and the native forest is very comparable, which is surprising given that it's deciduous, but as I've pointed out, only one of the species is deciduous and the others are evergreen. Okay, so, and I'm not going to show you a lot of soil evaporation data, but merely to point out that where you get high interception, you tend to get less soil evaporation because the canopy partitions water and radiation in much the same way. If it intercepts a lot of water, it also intercepts a lot of radiation and you get reduced soil evaporation. So in these 3 forest types on an annual time step, interception and soil evaporation add up to very similar numbers, okay? So the patterns are different and the contribution of those 2 fluxes is different, but they end up being, at least on an annual time step, roughly the same in all 3 forest types. Okay, now in order to estimate transpiration by a tree and then by a forest, we stick in a sap flow sensor, in this case heat ratio sensors, and we measure sap flux density, in this case at a single location under the cambium. And this is just the maximum sap flux density because it turns out through subsequent measurement that that point 10 millimetres under the cambium is the point of about maximum flux in all of these tree species. And this is the winter data. And not surprisingly, we can confirm that trees without leaves don't use much water. It's not zero though, which is really interesting. It's never zero. There is some evaporation through the bark, it seems, but it's very slow. Pinus here, Pinus radiata, lower, significantly lower sap flux density than either Payumo, which is the evergreen in the native forest, or Eucalyptus, which has the highest sap flux density, but is not significantly different from the Payumo. That's winter. Let's move on to spring. And the eucalypts shoot away. Significantly higher sap flux density in Eucalyptus than in the Nothofagus, which has woken up and now has a significantly higher sap flux density than the radiata. Okay. This is just sap flux density. It's just the speed at which water is moving up the stems of these trees. It's not transpiration. And by the time you get to summer, the ranking of the eucalyptus and the native forest species has reversed. Pinus is still ticking away at roughly the same speed as it has been the whole time. But now the sap flux density is lower in the eucalyptus than in the native forest species. And this is an observation that's repeated elsewhere when we try and do this. The eucalypt shoots away in spring, runs out of water on these shallow soils, and if the summer goes on for long enough, everything starts to come back together. But it usually doesn't, and there's usually a gap at the end of the summer, and we'll have a look at how big that gap is. And this is one of our Chilean students setting up a sap flow sensor with her safety hat on. Same safety hat that Richard often wears in the field. Right, okay, so I've just said that that's the sap flux density, but not all of the cross-section of these trees is conducting water, and we need to know how much is. And here you can see this green line here. The colours in these graphs are always the same. So green is always pinus, blue is always eucalyptus, brown, yellow or orange is always the native forest. If that helps you to see what's going on. In 20-year-old Pinus radiata, 68% of the cross-sectional area is sapwood, identified by staining. And in eucalyptus, that's 22%. And in Nothofagus, it's 52%. Okay, so there are different proportions of the tree that are actually conducting water. And these differences are highly significant. Now, we found that this is Amaryllis crucis, but we've got exactly the same slope for the native forest and for the pinus in Cuvolgo, 300 kilometres to the north. The pines were exactly the same at age 20, and the native forest was exactly the same slope, which was handy. Oh, and having said that, now there it is. Okay, I did have a graph for that. All right, but these are 20-year-old plantations, and at age 7 in Eucalyptus globulus and age 9 in Pinus radiata in the same area, the slopes are still significantly different, but they're also a lot higher, a larger proportion at and around canopy closure or just soon after is sapwood than later on in the life of the plantation. And if you look at the published data, we sort of have developed different exponential decay relationships for the different forest types with forest age. So you can come up with a sapwood area index for pretty much anywhere in the plantation estate, which you can use to calculate the water balance of the forest. Now, I've said that we only measure at one position in the sapwood. Now, it's often assumed, or standard allometrics relationships are applied, or it's assumed that the flux density is the same across all of the sapwood area. Well, it's not reasonable really to expect that it's going to be, because the leaves that are connected to the sapwood towards the centre of the tree are more shaded than the leaves that are connected to the sapwood towards the outer part of the tree. Oh, and this is one of our friends. Here we go. Can you see my cursor there? When you lift up the sap flow sensors, these spiders, which are as big as your hand, often emerge from underneath the sap flow sensors. They're completely harmless, but they're terrifying. And everyone does the fire spider slapping dance when they see them. Okay, so we made up some sensors which had thermocouples at different depths under the cambium, and we stuck them in trees of the same species. And while you're looking at transpiration data from 2017 and 18, this was actually done relatively recently. So it's only been applied to the data in the last week, and I'm about to show you that. So what you find is that in Eucalyptus globulus, you get a relatively steep decline of velocity with depth. You get a slower decline and a significantly slower decline in Pinus radiata, and the other native, and this is one of the native forest species, that's Peumo, and this is Nothofagus, which is, it has a similar pattern to globulus. So we need to this is really important. We need to take account of this in coming up with estimates of transpiration in these forests, because it has a profound impact on, what is the area weighted sap flux density of these trees. So we've applied that, and I've actually done a sort of a crude sum here. If you apply that relationship to different annuluses in different sized trees, you end up with a relationship between a sort of an area weighted correction factor and tree size. And these are different relationships for Pinus, native forest, and Eucalyptus globulus. And that happens, and you get this reversal of these lines because the sapwood area is so much less in the eucalyptus. So there's not much sapwood area in those inner annuluses where the velocity is lower. Okay, so that's why you get that kind of reversal of those lines. So we've applied that and come up with, this is measured, well, calculated sapwood area from measured basal area, and the pale lines are uncorrected, okay? The dark bars are corrected for these radial profiles, okay? And the correction is very small in eucalyptus, similarly small because you've got a bunch of really small trees in native forest, but quite large and as much as 30% in pinus. And that has a big impact on the water balance that you calculate. So it's really important that you do that. Am I going for time, by the way? Oh God, okay. All right, so, okay, all right. I didn't realise we'd gone quite so far. All right, so now I'm going to show you transpiration calculated for these forests. And so this is a cumulative difference between two forest types. So when, for example, with this pine line, when it's going up, the pine is using more than the native forest. When it's going down, the native forest is using more than the pine. And this is the kind of pattern that we see repeated over and over again in these forests, is that in spring, now what happened here is that we just, at the end of a mega drought, the eucalyptus actually took a little while to get going. They'd been really hit by the drought. They needed to recover. And once it started raining, they did eventually recover, but they were a bit slower. Okay, and you get this higher rate of transpiration in both of the plantation species in spring, and then the native forest actually starts transpiring more water once you get into later summer. And the longer you go, the closer they get together, but they never quite meet up in any, oh, hang on, there we go. This is the same graph, but this is cumulative ET. And you can see that cumulative, again, you get this spring difference between the native forest and the plantations. The big difference occurs when the canopies of the nothofagus are regrowing and the conditions have got warm enough for the other species to transpire. And because these are shallow soiled systems, they all run out of water in the end and start coming back together. Okay, all right. And this is just a graph of actual cumulative ET showing that the eucalyptus and the pinus end up in a very similar place in these forests. So the concern about eucalyptus compared to pinus in these shallow soils, and that's an important caveat, is not reflected in these observations. And I know that this has been an experience of other researchers in Chile, that they can't reproduce the hysteria about eucalyptus. But it's pretty clear that plantations over a year, and this is years data, use about 150 millimetres more water than the native forest, and that difference is similar for the pinus and the eucalyptus. Okay, all right, there, and there's the totals. Okay, all right, so let's move on. In the drier climates, very similar pattern. Again, this is the difference, and ignore the eucalyptus line and just look at the pinus line, because I don't have really enough eucalyptus to draw that line, but I've just drawn it anyway. But the pine line is very real. And again, you see here you got some late rains and things sparked up again. But again, you see that when you get later in the season, the native forest is actually using more water than the plantations, and they close up. But in here, by the time you get to the end of our 7 months of measurements, when all of our forests and sensors were incinerated, the difference was about 50 millimetres. But that is a larger proportion of annual stream flow than the 150 millimetres in the forest in the central region. Okay, so water balance of three forest types, Morellus crucis, and here you can see transpiration, interception and soil evaporation, and you can see that the sum of interception and soil evaporation is very similar amongst the three forest types. So it's transpiration that differs between the forest types, not the sum of the other fluxes. A very similar story in Cavolgo. Again, ignore the eucalyptus, but again you have pinus using significantly more water than the native forest, though the difference is smaller. It's a drier system, but again a very shallow soil. And I don't have native forest. This is down where the rainfall is about 2,000 millimetres. And again, I can't find a difference between young pinus and young eucalyptus. But again, you can see here that the fluxes are much higher, partly because the soil is a lot deeper. It's a lot more fertile. It stores a lot more water. It's a lot more loamy, and the rainfall is much higher. And they're younger forests. Okay, so then this is the same graphs, but expressed as a proportion of rain. And here you can see that evapotranspiration is a much larger proportion of rain. And if you assume no change in storage, this gap is stream flow. There's much more room for stream flow in a catchment covered by native forest than there is in a catchment covered by pinus plantations. When you get to Morelos Crucis, there's still a lot of rain left over once you account for all the ET. So if you have a reasonable water storage infrastructure, which you don't in a lot of locations, then there is actually plenty of water. But you may have some low flow issues when you get to summer if you've got local water extraction by rural communities. And that's an issue that Arauco is grappling with now in its dialogues with those communities. Okay, forest growth. Pinus is growing slightly slower on average. This is just annual increment over a year. There's a lot of variability. The dark lines are the plots that we selected for our water balance plots, and they cover the range of productivities represented in each forest type, purely by chance, as it turns out, but it actually looked okay in the end. I now want to put all of that together and calculate wood production, in this case in mass, not in volume. Okay, so I've made some assumptions about wood densities. We've actually measured some and calculated some transpiration efficiencies, and these are going to be very important calculations when we come to try and work out, you know, what area is required to generate the stream flow, and at the same time meet the carbon sequestration requirements of a move towards carbon neutrality in these regions. And these data will be, you know, very important in informing that process. Transpiration efficiency and wood production per evapotranspiration are higher in the eucalyptus and the pinus, but there's a lot of variability and the difference is not significant. But eucalyptus is significantly more water use efficient than the native forest. I won't go into that at this stage. So I'm just going to give you a bit of a summary of what I think the major points are. So sap flux density is greater in broadleaves than in pinus, okay? Pretty much throughout the year. And that's true of both native forest and of eucalyptus forests. The highest values of sap flux density occur in the eucalyptus in spring compared to the other forests. In spring, water use by eucalypts exceeds water use by pines, which exceeds water use by native forest. By the time you get to late summer, water use by native forest exceeds water use by pinus, which exceeds water use by eucalyptus. That's about the ranking of ET by the time you get to late summer. But nonetheless, on an annual time step, plantations use more water than native forest. And in the year that we measured, that difference was 50 to 60 millimetres in the northern forests of Cavolgo and about 150 millimetres in the central forests. But in the central forest, there was still a big gap between ET and rainfall. Pines use more water than native forest due to a greater sapwood area than native forest, okay? Whereas ukes use more water than native forest due to higher sap flux densities. So the mechanisms are quite different in those two forests. They also make them, give them different vulnerabilities to mortality during drought, but that's a whole other talk. Overall, pines and ukes on an annual time step, whether they're young or old, seem to be about the same, except perhaps when the pines are very young or in circumstances where you have very deep soil, and that still has been the South African experience. I know on very deep soils, they got quite large differences between eucalyptus and their impact on stream flow compared to pinus. That hasn't been our experience in Chile, and it hasn't been the experience of others who've worked on this issue in Chile. There are different seasonal patterns, and Rich is going to talk about those a lot more in the next talk when we try to come to grips with using modelling approaches, generalising these results to understand what the likely impact is, particularly on low flows. And that's it. Ukes are more efficient, that's it. And if you want information on this talk, it's all there in the last slide. I can give you information on the talk. Francisco can give you information on the hydrology program, and Pablo's the guy to talk to about the ecosystem management research. And I'm sorry I've taken a bit too much time.
Spot on. Thank you.
Yeah.
Great. Thanks very much, Don. That was yeah, very interesting. I might just see if I get any.
Is anyone still awake?
That's Jason Barringer.
See you, Jason. In the winter, yes. There's plenty of radiation in summer. The forests, but when you get further south, once you get to Valdivia and further south, rainfall is 2,500 millimetres and potential evaporation is about 900 millimetres. So you're getting into energy limited systems when you get down there. And that's why I didn't talk about it today, because it's, there's so much water, everyone's drowning. People are growing mold in their, living rooms, and they still protest about it, but
So you mentioned
Yeah.
earlier in the talk the drying trend, and I wonder how that plays into this. So it seems like you've solved the puzzle to some degree around plantations versus native, but now you've got this other driver of change.
And inevitably, that's that's the realm of scenario analysis using models that we're calibrating and parameterizing. And Richards will talk much more.
Plug for one of our
that's a plug for the future talk.
By,
It's also, I'm now working in New Zealand, and one of the things that we've shared between the projects is the data, because they're grappling with the same issue, a push towards carbon neutrality by 2050, the need to sequester more carbon, to manage the impact of that on water resources, and they're dealing with Pinus radiata and a lot of beach-dominated native forests. So they have a lot of similar questions. So we're using this data to calibrate the models that we're using in the New Zealand project so that we can get ahead of the game there. So that's part of that work as well. But that's all about scenario analysis.
Question here from Alina. What about the humidity that brings a native forest, which is more than eucalyptus? Because native forest gives more shade.
Yes, that has a big impact on soil evaporation, and you can see that in the soil evaporation data. So the evaporation from the understory and from the soil and from the litter is much higher in the eucalyptus forests than it is in the other forest types. That's the major difference. Certainly that's true in the comparison between eucalyptus and native forest, but Pinus has a pretty dense canopy too, and it's pretty dark and cold under those forests as well.
There's a second part to the question there. What about the acidity that eucalyptus could bring, which potentially could restrict other natives?
Well, I'm not a soil scientist, but I know a guy called Sedana Nambiar who gives a talk on myths about eucalyptus and Pinus plantations, and one of those is that they acidify soils. And there's absolutely no empirical evidence for it globally, as far as I'm aware.
Sorry for a non-forestry person question, but which eucalyptus are these? Are they like
well, it's worth answering it this way, I think. So there are 600 eucalyptus species, thereabouts. The plantations of the world, the 25 to 30 million hectares of them now, eucalyptus plantations are 9 species from one subgenus.
Right.
That clings to the wet fringes of Australia. So they're not representative of eucalyptus in any ways. So in this case, it was Eucalyptus globulus. Yeah. They're also growing Eucalyptus nitens. So Eucalyptus globulus is grown in the warmer and drier areas. When you get further south, it gets too cold for Eucalyptus globulus. There's a bit of snow about. And so they grow Eucalyptus nitens, but the wood is nowhere near as good. They're now planting a hybrid called Glony, which is a hybrid between globulus and eucalyptus, and they have a lot of emphasis on that in their planting programs now, and that's about, so globulus, I saw a talk given by a guy called Nuno Baralo once, he said that all of the work in tree breeding in eucalyptus around the world is about growing globulus wood on non-globulus land. So globulus is the premium pulpwood species. There is, and with daylight second. So, and that is exactly the same in Chile. It's about trying to grow globulus on colder land. Right. You know, globulus wood on colder land. That's what all the hybridization is about.
So with the I guess the issues the community had, is this new science that you're sort of just summarized for us, has that helped, I guess?
So what was the question? I was reading something, I apologize.
Basically, you preface this by saying there was some worry by the community about the plantations. Has this new data and scientific outputs from this,
I think it helps. I think it helps a lot. You know, Richard and I had an experience where we were with a community group in the field, and Arauco is very conscious of this now. You know, and this has been a changing attitude in the forestry sector. Is that the best way for them, you know, to sustain a social license is to have an open dialogue about the data and to share the data. So that's sort of the new philosophy in the company. And when we went to a community meeting, we were asked, you know, do plantations take more water than the native forest? And we just said yes. And their assumption was that we would obfuscate and lie about it. And they said, but you haven't answered our question. And then someone said, no, he did. He said yes. Sorry, you said yes. You know, so, and there's a real relief. Oh, okay, so now we can have a real conversation. We can stop pretending that they're not different. You know, yeah. So, and that's been really powerful, I think. Yeah.
Don't they grow these through for timber rather than for paper?
Eucalyptus are grown for paper primarily. They have several large pulp mills, one in the country, one in 3 big ones, in fact. They also, the pinus is grown primarily for structural timber products, veneers, engineered lumber products, all of those things. So they have something like 30 processing plants around. It's more than that, actually. I've probably underestimated that.
You were saying that 20-year-old globulus there.
Yeah, that's right, and that's yes, that's true. And so, yeah, there was a lot of debate about that when we did it. And in fact, what we did was we inherited a bunch of plots and we just worked in them. And I guess we reasoned in the end that at least it would give us kind of an end member, you know, for the growth curve. And we did, I showed you some measurements from some younger forests, and the fluxes are much higher. But again, the eucalyptus and the pinus are comparable. Yeah, but yes, you're right. It's and that's the tricky thing. And again, that becomes a modelling project where you're trying to. So what happens if and Richard's done some scenario analysis around what happens if you shorten the rotation length because there's a push to shorter rotations. What does that do to the water balance? In fact, it makes more water available because there's more time regrowing canopies. What happens if you have fewer trees per hectare? What happens? So all of those scenarios are being modelled.
What about the fire risk of the 3 different forest types?
Yes. Now, I'm not a fire expert, but we did have a big fire, and there was a publication, and I've seen Mike Ryan give a talk about that, and there is evidence that I think that there was, and someone may correct me about this, but there was greater fire intensity on those eucalyptus plantation sites, but the fire does slow down pretty quickly in a plantation also because it's less able to sustain a ground fire than a native forest. So it swings and roundabouts a bit with fire.
Got one more question here for you, Don. Is the drainage below the root zone of relevance here, given that in WA, some eucalypts crack and fracture the soil rock and transmit water down?
Now, that's a big question. Look, and we have really pushed to, we've been making all of these measurements in the forests, And it's really difficult to work in those soils and to drill holes and to do all that kind of thing. And we have done some of it, and we are measuring groundwater depth and soil water content. While we say the soil is very shallow, there is evidence, if you look at cuttings, that older forests do have roots down to 2 metres or so, about that. So they do put roots down into that rock. There's not much evidence of them going much deeper than that. And there's if you look at these catchments, there's a big pile of that rock between the root zone and the groundwater. And one of the real difficulties that Richard has had is if you treat a forest as a single cell, and you try and say, how does the catchment behave if we treat it as a single cell? All the water drops out and becomes drainage straight away. You have to slow that down enough to reflect the dynamics of stream flow. All our models do a pretty good job of the annual water balance, but the dynamics of stream flow is much more difficult. And the effective soil water, it's the sort of depth. So what you've got is you've got this shallow soil, but you've got this zone of permeable, partly weathered rock that water moves through to the groundwater, and getting the speed of that water movement right is the great challenge of modelling these catchments. And Richard will tell you all about that in the next talk.
Great. Well, thank you very much for your time.
It's a pleasure.
I think we'll wrap it up there. And we really appreciate you coming down and sharing with us your wisdom about Chilean forests.
My pleasure.
Like I've learned an awful lot this afternoon.
Great. Thank you. Okay.
Thank you.
All right. That said, are we off?